Hello! Today I will show you how to set up a simulation using CENOS induction heating software. Since I have already created a CAD file, I will use the Import CAD option to select this file. CENOS supports either STEP or IGS formats. The CAD file processing might take longer if the file is big. Once the CAD file has been processed, CENOS will ask if we want to create an automatic air domain. Since my CAD file has only the geometry and not air, I will choose yes. Then I have to select the coil terminals so that CENOS knows where to cut the air plane, since terminals have to be on the same plane as the air borders. After that, we click Create Air. The air generation might take longer if the CAD file is big. When the air has been generated, CENOS will ask us to assign geometry roles. As you can already see, the inductor has been automatically assigned based on the selected terminals before air generation. Geometry roles are necessary to make the simulation setup easier for the user, because based on geometry roles, some automatic assignments will be made by CENOS. For example, the inductor will have copper set as material and the possibility to input power, current, or voltage. So here I can select the workpiece and assign it with either a double click in the visual preview or by selecting the solid in the list and clicking Assign. For this role, CENOS will make sure that thermal analysis is enabled, for example. After that, I need to assign the workpiece surface. I can filter by the workpiece to make sure that I do not miss any faces, and then I can click Select All and Assign. For this role, CENOS will make sure that the correct boundary conditions are enabled, for example for thermal losses or cooling. Then we can see that CENOS warns that some geometry solids have no roles selected, and in the visual preview we can see that those are fluxes. So here I can select the drop-down menu and choose the role Flux Concentrator. Then I can either select all of the solids in the list, or I can hold down Shift or Control and select all of the solids in the visual preview and then click Assign. Then we can see that the Physics tab has been enabled and we can continue setting up the simulation. The first thing in the Physics tab is the overall simulation setup. Here we can set the working frequency, which for this case is 10 kHz. After that, we need to set the end time, which is how long would the process take in the real-world time. Here it would be 10 seconds. Then we need to choose the time step. A time step discretizes the total time. The smaller the time step, the better the results. However, it will take longer to calculate. For example, I can set the time step as 1, which would mean that the total 10 seconds would be divided into 1 second segments, and I could see the results for 1 second, 2 seconds, 3 seconds, and so on. Here you might notice that if you expect the heat to change faster, the calculation results might be incorrect, as the calculation will jump over quite a lot of time. Also, if you have any kind of movement, then a too big time step might also jump over some motion. If you do not want to set a single small time step for the whole calculation, for example, you know that you need a smaller time step in the beginning, but it can be larger later on, you can set the time step as a table. Here you need to choose the start time and input the desired time step. For example, 0.2. Then choose the end time for this time step. For example, I want to have 0.2 for the first 3 seconds. Then I would input 2.99 and 0.2, because the table should have start and end times for each value. And then input 3 as the start time for time step, for example 1, and 10 as the end time. If you do not specify the end time, the time step will gradually grow instead of being constant. I input 2.99 instead of 3 as the end time for 0.2 because I want to have 1 as time step right from 3 seconds. If I had input 3 as end time and for example 3:01 as the start time, the time step of 0.2 would reach 3 seconds and see that it should still be 0.2, so it would continue with the same value and only switch to 1 starting from 3.2 seconds. If you are not sure how big of a time step you should use, you can also choose an adaptive time step. Note that it cannot be used if you have any table inputs, for example, for the inductor power. It also cannot be used with complex motion, since it might jump over some motion and that would lead to incorrect results. An adaptive time step starts at 0.01, calculates the results for that time. Then it takes a bigger value for the next step and calculates the next results. Then it compares the results. If the temperature dynamics are too big, it will take a smaller value and recalculate the results for that time step until the temperature dynamics are okay. You should also note that you cannot predict how much time the calculation will take with an adaptive time step. Overall, choosing the time step is an iterative process. If you are not sure what value you should choose, start with a larger value and calculate some part of the simulation, and then check the results. If there are some temperature jumps or any other weird results, try a smaller time step. Here I will input 0.04 as a constant time step. If you want to define motion, you can do that from the Motion tab. Here you can click Create New Motion. Then you will need to choose between simple or complex motion. Complex motion is when the geometry is actually moved and you will be able to see the motion and results. Simple motion, however, only moves the temperature field, not the actual geometry. This is why it cannot be used for all cases. If you want to use simple motion for rotation, your geometry has to be axially symmetrical around the z-axis. If you are not sure what type of motion to choose, please reach out to our support. For this case, I will use complex motion. I want to move the inductor and the fluxes, since they are one on top of the other. After that, I have to define the motion speed. Scanning motion is defined in meters per second, but rotational motion is defined as radians per second. I want to use rotational motion as 14.5 radians per second. When you input any motion speed, make sure that the time step will be able to capture it. If your time step is too large, CENOS will warn you when you try to run the case. Please note the warning and try to reduce the time step to not have any weird results. You can also see that there is a new Create Motion button. You can add another motion as well. However, make sure that this new motion is defined for a different domain. For example, I could add scanning motion for the workpiece and have it move upwards. If I wanted to move the inductor and fluxes downwards, I could just add scanning motion to the existing motion here. In the Inductor tab, you can see that electromagnetics have been automatically enabled, as well as copper has been assigned as the material. If you want, you can change that by either clicking Select and choosing a material from our database, or you can add a new material. Next, you can define which terminal is the ground plane and which has an input. The input can be either power, current, or voltage. You can input a constant value, a table value, or an expression. For this case, I want to add power as a table. As mentioned before, I need to add start and end times for each value that I want. I want to have 110,000 watts for the first 3 seconds, and then 0.1 watts from 3 seconds. So I would input 0 and 2.99 as the start and end times for 110,000 watts, and then 3 and 10 for 0.1 watts. It is not suggested to input 0 as it might cause some issues with the calculation. However, 0.1 is absolutely okay and it will act as a 0 in results, so the results will also be accurate. Then we can go to the Workpiece tab. Here we can see that thermal analysis and electromagnetics have been automatically enabled. We need to choose a material. As I mentioned before, you can either select an existing material from our database or create a new one if you know the properties. I will choose an existing medium carbon steel material. I will also want to see hardness values and phases for my workpiece, so I will enable these two calculations here. Note that with these calculations enabled, the full simulation will take a little bit longer to calculate as there will be extra results. Next, we have the thermal analysis section. where we need to specify what exactly happens on the workpiece surface. We see that the default is cooling with natural air. We can choose other options, for example, convection or combined. Here I will leave cooling, however, I do not want natural air cooling. So I will choose cooling with quenching. Here I need to specify the heat transfer coefficient. It can be either a constant value or a table value. I want to use a table value and I will choose one of the predefined values here, PAG 20% spray quench, and click Apply. Next, I want my cooling to start at 3 seconds. I will leave static, however you can also specify a shower motion, and I will specify the shower width as 0.09 meters. The direction will be in XY plane, and the shower center offset will be 0.076 meters, as my geometry is not exactly on the coordinate center. If you want to learn more about setting up cooling, please refer to our documentation page or reach out to our support team. Next, we can see that for electromagnetics, everything has been automatically assigned. For the air, we can see that nothing is required. All of the fields have been assigned automatically. Next, we need to choose the material for the flux concentrator, which I will choose as Fluxtrel 50 from our library. At this point, you can click Run and the case will start calculating. If you have not saved the case yet, before running, CENOS will prompt you to do so. If you have CENOS Simulation Manager, you can also click Add to Queue to run the case from the Simulation Manager. In both of these cases, CENOS will generate an automatic mesh for your case. If you do not want to run the case with the automatic mesh, you can also go to the Mesh section and refine it. You can enable mesh refinement here, and CENOS will ask if you want to keep the existing mesh. Here we will choose to keep it. Then you can see a tab for each of the solids, and you can click on them to specify some values for each geometry role. For example, I can choose the workpiece and change the element edge length, which specifies the largest edge length possible for the mesh elements. You can change the thickness of skin depth, just make sure that it is not too big or it might cause issues with the mesh generation. You can also change the number of skin layers and the stretch factor. If you want, you can also select some faces or edges in the visual preview and change the element edge length for those faces or edges in particular. You can also click on More Properties in the main mesh window, where you can change some more parameters for the whole mesh. You can change the surface and volume gradients, as well as curvature safety. Once you have set all of the parameters as you wish, you can click on Generate Mesh. For larger or more complex geometries, this might take a bit longer. After mesh generation, you can see the full mesh size here, under the Regenerate Mesh button. You can also see the mesh size for each of the geometry roles here. Note that mesh size directly correlates to the calculation time, so the larger the mesh, the longer the calculation will take. If you get a warning about the mesh exceeding a certain number of mesh elements, please make sure to change the mesh settings to lower the number of mesh elements. Otherwise, your computer might not have enough resources to run the simulation, and the case will crash. Similarly to the time step, mesh generation is also an iterative process. If you see some weird results, try to refine the mesh to have smaller elements and run the case again, if your computer resources allow it. If you are satisfied with the mesh, then you can click Run or Add to Queue. If you want to learn more about meshing, please refer to our documentation page or reach out to support. You can access the support chat here under the orange icon on the right-hand side. Once the case has finished calculating, CENOS Results Viewer will automatically open. However, if you have closed the results, you can easily access them again from the desk view by clicking the Visualization button. After clicking Play, we can see the complex motion of the geometry. You can select a specific moment of time to see the results by either using the slider or choosing a specific value in the drop-down menu. You can also rescale the values or change the colors here under the gear icon. There are all kinds of results that you can see. I will show some of them. For example, we can use the slice filter to see a 2D section of our geometry. You can also change some settings for it here on top. It can be exported as an image as well. Then, we can disable the visibility for the inductor and fluxes to see the workpiece better. And we can use the clip filter, which will cut the geometry on the specified plane, and disable toggle plane. On this clip, we can use the temperature probe filter to see the temperature changes on a specific point. So here I press Add Point in Geometry Preview. Note that you can also use it in the slice view. Then I select a point and the temperature probe will be generated. You can add multiple probes if you want, and you can export this graph as an image as well. For this calculation, I had enabled phase calculations and hardness calculation as well. You can see those values here on the left, where you select the workpiece. I can select hardness values here, and in the 3D view we will see them. Then you can select the hardened profile filter to see where austenization temperature has been reached. To see the profile better, you can disable the visibility for the workpiece. Next, we can use the clip filter on the hardened profile filter. We can use the ruler to measure the depth of the profile. You can select and move these endpoints of the ruler, and by default they will snap to the closest mesh element. Here we can see that the profile depth is around 3 mm. Next, you can see that there are multiple tabs for the results. Each of the tabs has some specific filters already enabled to ease the review of the results. In the Workpiece tab, you can see all of the filters I already used in the Heating tab for the workpiece. However, you can see that they have been automatically enabled. In the Magnetic Field tab, you can see the magnetic field enabled by default. In the Phase and Hardness tab, you can see the hardened profile enabled. In the Inductor and Flux Concentrator tab, you can see the current density for the inductor enabled. Here we need to go back to some 3 seconds, because as you remember, after that the power on the inductor is nearly zero, so there is no current density. In the performance plots, you can see some extra values, for example, the active power, the inductance, impedance, and other parameters. All of these results can be exported under the Export Results drop-down. For example, the current 3D view can be saved, the performance plots can be saved as images, as well as animations and spreadsheets. Thank you for the attention.